Assalamualaikum warahmatullahi wabarakatuh and a very good day. My name is Zul Asnawi and I'm from group CE3i along with Farizah Rosaidi, Nurul, Fatihah, Asyikin and Nordania, Dayana, Noradlan. So for integrated project Jan20 consists of subject reaction engineering and fundamental of reactor system and separation system 2. So I'll be presenting about the reaction engineering and fundamental of reactor system, which consists of type of reaction, reactor design and type of catalyst used, material balance and reactor sizing, how our reactor works, and strategy to maximize selectivity and yield of H2. Okay, so firstly is that I want to talk about the type of reaction in our design reactor. So there are two types of reaction. The first one is the steam methane reactor, SMR reactor, where the chemical reaction occurs here is that methane reacts with water, producing carbon monoxide and 3 mole of hydrogen. So this is a chemical synthesis for producing syngas, which is H2 and carbon monoxide, CO. Okay, so in this SMR reaction is actually occurs in high temperature, which we set as at 100 degrees Celsius, and in medium pressure, 30 atm. Okay, so this is actually an endothermic reaction where high temperature are more favorable. Since there is a volume expansion occurs, so low pressure are more favorable in this reaction. So the assumption for the first reaction is that the steam and water inlet, the feedstock of steam, is in excess and it is constantly supplied to the system. Okay, so the next assumption is that the composition of inlet natural gas are 98% of methane and 2% of carbon dioxide. So this inlet of natural gas is actually after it has been desulfurized, before it is entering the SMR reactor. Okay, so the next one is the water gas shift reactor. So in water gas shift reactor, WGS, the chemical reaction is carbon monoxide react with H2O, producing carbon dioxide and hydrogen. So this chemical reaction, which occurs in WGS, is actually further converts the CO to CO2 while generating H2 also. So this reaction favors low temperature and medium pressure, and it is also an exothermic reaction which favors low temperature generally. However, we assume that this WGS reactor contains high temperature shift and also low temperature shift. Why high temperature shift is because thermodynamically it prefers high temperature, but in kinetically it prefers low temperature. So we give two shift here, high temperature and low temperature shift. Okay, and also the outlet stream of the WGS reactor undergoes water removal unit before entering the absorption unit. So meaning the wastage of water that they don't use is being removed first before entering the absorption unit. So the next part is the reactor design. So the design we choose is the catalytic tubular reactor. Why catalytic tubular reactor? Is because firstly, it is a combination of plug flow reactor and also packet bag reactor. PFR and PBR combines into this catalytic tubular reactor. And this reaction, the reaction occurs inside tubes packed with catalyst. And also the flow through of the reactor is in high velocity, so that there will be no side reaction. When there are no side reaction, there will be higher yield for H2 production. And also occurs in continuously, and it has low operating costs. But however, the disadvantage of this catalytic tubular reactor is that it is hard to be cleaned. So yeah, but however, it is more convenient than any other reactor there is. Nextly is the type of catalyst used. So in the first reactor, which is the SMR reactor, we are proposing to use nickel catalyst. Why? Because it is an active metals which promotes SMR process. Besides that, it is also in high reactivity and also have low attrition. Attrition is low erosion lah. And also it can also withstand high temperature, which is the characteristic of SMR, and also it exhibits good mechanical strength. However, the disadvantage is that it is expensive. So what we can do is that we can use lower percentage by using nickel and also aluminum oxide together. Okay, so the next one is the WGS. In WGS reactor, since we assume it to have HTS and LTS, therefore in the HTS we will be using ferrum oxide catalyst because it favors high temperature. Same as also the nickel catalyst, it gives good mechanical strength. Okay, the next thing in the LTS we are proposing to use copper oxide because it favors low temperature. Okay, so for the material balance and reactor sizing, so the first one is we go through the SMR reactor first. So as you can see here, what we did is that we did a stoichiometry table first, and then by doing the stoichiometry table, we can determine the flow inlet and also the outlet of the whole component. And then by listing all the three equations, which is the mole balance equation, rate law equation, and the stoichiometry equation, we can combine it to find the total weight of the reactor. Since this is more towards a packet bag reactor, so the weight of the reactor determines the reaction lah, because the reaction occurs in the catalyst. Okay, so the rate law, as you can see here, the rate law we assume it to be zero order because we referencing from other journals. Okay, so and we found out as the volume of reactor to be 5.69 m3. Okay, so for next one is the WGS reactor. So using the same method for SMR reactor, firstly we construct a stoichiometric table first, and then we list down the equation. After listing down the equation, we can find the weight of catalyst, and then by finding the weight of catalyst, we can find the volume of reactor. So volume of reactor will be 232.52 m3.
Hi, my name is Nurul, and today I'll be explaining about how our design reactor works. The conventional SMR process used in industries consists of two main steps. The first step is SMR, steam methane reforming reaction, and WGS, which is water gas shift reaction. In the first step, endothermic SMR reaction takes place at a high temperature of 800 degrees Celsius and medium pressure of 30 atm, which produce carbon monoxide and hydrogen. Normally, the subsequent stage of the SMR process includes WGS reactions, which further convert carbon monoxide to carbon dioxide while generating more hydrogen. In the first stage, where a high temperature shift reaction is taking place, the gas is mixed with steam and passed over an iron mixed oxide catalyst at a temperature of 300 to 450 degrees Celsius in a fixed bed reactor, which decreases the carbon monoxide concentration down to 2 to 3%. In the second stage, the low temperature shift reaction, the mixture of gases is passed over a copper or zinc oxide catalyst at temperature of 190 to 220 degrees Celsius, where the carbon monoxide concentration is reduced to 0.1 to 0.2%. For further hydrogen purification can be achieved using methanation or pressure swing adsorption, which also known as PSA. So next, I'll be explaining about the strategy to maximize production of hydrogen. My first point is increase the temperature. So from the graph, we can see that with the increasing of reaction temperature for the conversion of methane, the yield of hydrogen increases. More methane will be consumed, hence more hydrogen will be produced. Increasing the temperature of a system in dynamic equilibrium favors the endothermic reaction. The system counteracts the change that is made by absorbing the extra heat. The second point is decrease in pressure. It is also shown that as the pressure decreases, the yield of hydrogen increases. According to Le Chatelier's principle, if pressure is increased, then the equilibrium shifts to the side with the fewer number of moles of gas. But if the pressure decreases, the equilibrium shifts to the side with more number of moles of gas.
A study states that if several components need to be separated from a gas mixture, two or more types of adsorbents can be utilized for adsorption process, depending on the property of the adsorbents. In this case, we want to separate other gas components from hydrogen gas, such as carbon dioxide, carbon monoxide, and methane. According to a research, activated carbon and zeolite molecular sieve can produce a maximum 99.999% of hydrogen purity. Zeolite 5A and 13X are two common zeolite molecular sieve adsorbents used in a PSA system. Studies show that zeolite 5A has a higher adsorption capacity for carbon monoxide and methane compared to zeolite 13X. Thus, the types of adsorbents used in this project are activated carbon and zeolite 5A. This combination of activated carbon and zeolite is used in each column because activated carbon is more inexpensive and more economically than zeolite. Activated carbon also has high adsorptive capacity due to high surface area, pore volume, and pore size distribution. Other than that, activated carbon is able to adsorb carbon dioxide, meanwhile, zeolite is mainly high-performance adsorbents to adsorb components such as methane and carbon monoxide. Experimental results indicate that activated carbon should be used as the primary layer, which is at the feed entrance. Meanwhile, zeolite will be the second layer of the adsorbent for hydrogen purification in PSA system. Carbon dioxide, methane, and carbon monoxide can be adsorbed in this first layer. The remainder of methane and carbon monoxide will be further adsorbed by the second layer of zeolite. From the article, we obtained that the experimental scale of the total bed length of activated carbon and zeolite 5A used is 100 cm, where the ratio of the carbon to zeolite is 0.32. By the ratio, we get that the experimental scale of the bed length for activated carbon is 24.24 cm and zeolite 5A is 75.76 cm. This is the schematic diagram of the multi-column PSA unit. The cyclic adsorption-desorption processes carried out in the adsorbers A1 to A4. The PSA process works at basically constant temperature and uses the effect of alternating pressure and partial pressure to perform adsorption and desorption, which will be explained later in the strategy part. Few assumptions have been made for the adsorption column in the PSA system, which vary in the equations that will be later used in the project. First, the flow pattern is described by the actually dispersed plug flow model. Next, thermal equilibrium is assumed between fluid and particles. Other than that, the mass transfer rate is represented by a LDF model due to resistance between the gas phase and solid phase exists. The gas phase also behaves as an ideal gas mixture. In addition, the radial concentration and temperature gradients are negligible. Finally, the equilibrium adsorptive quantity is estimated by using the extended Langmuir isotherm equation. In isotherm equations, Langmuir model equation and extended Langmuir-Fenlich isotherm LRC equation will be used to determine the isotherm graph of the gas components. Here are the parameters obtained for each gas components from research. We can observe both tables for Langmuir coefficients and LRC coefficients used for the activated carbon and zeolite 5A. Based on the equations and parameters, both Langmuir solid line and LRC dash line isotherms are plotted for each gas components on activated carbon and zeolite. Based on the graphs plotted, we can observe that the adsorbed amount of components on zeolite 5A has been well estimated by the LRC model. Meanwhile, the Langmuir model showed better results to fit the adsorption data for activated carbon. This is because the stiffness of gas carbon dioxide and carbon monoxide reduced at higher pressure, so with the aid of exponent and in the LRC relationship, the experimental results on zeolite 5A can be matched more precise for this LRC model. Since the highest adsorbed capacity of gas components in both adsorbents is carbon dioxide, the breakthrough curve of carbon dioxide is chosen to represent all the gas components in the multi-component mixture. Figures show the breakthrough curve of the carbon dioxide for activated carbon and zeolite 5A. Moving on to the MTZ calculation for the experimental scale data. Here is the MTZ calculation for both activated carbon and zeolite adsorbents. The bed length of activated carbon is 24.24 cm and zeolite 5A is 75.76 cm. From the previous breakthrough curves, the TU and TT are obtained where for activated carbon the TU is 13 minutes and the TT is 23 minutes. Meanwhile, for the zeolite 5A, the TU is 17 minutes and the TT is 27 minutes. The fraction of the total bed capacity is calculated where we can calculate the used bed length HB, which is equals to TU over TT times HT. The HB for activated carbon is 13.7 cm and zeolite 5A is 47.7 cm. Finally, the unused bed length HUND or MTZ is calculated by subtracting the HB from the HT, where the MTZ for activated carbon is 10.54 cm and zeolite 5A is 17.67 cm. Here is the MTZ calculation of scale-up application. The new full-scale total bed length is 730 cm with 0.32 carbon to zeolite ratio. Based on the ratio, the new bed length of activated carbon and zeolite 5A is calculated. Since the diameter of the column is constant for the experimental and full scale, so the MTZ should be the same. Thus, the new length of activated carbon bed is 176.97 cm and zeolite 5A bed is 553.03 cm. With the same column diameter, we know that the MTZ should be the same for both experimental scale and the full scale column. The MTZ for activated carbon is 10.54 cm and zeolite bed is 17.67 cm. Therefore, the new HB prime can be calculated where the new bed length minus the constant MTZ. Then, the new breakpoint time can be obtained by the following ratio: HB prime over HB equals to TB prime over TB. Thus, the new breakpoint time for activated carbon bed is 157.93 minutes and zeolite bed is 190.8 minutes.
Moving on to the CO2 removal unit. For CO2 removal, an absorption stripping column is used to get higher composition of hydrogen that will be fed to the hydrogen enrichment unit. An absorption column with 90% efficiency is used to remove solute, which is carbon dioxide, from the feed gas mixture onto a non-volatile liquid or solvent. In this case, monoethanol amine is used as the solvent. Next, to get higher percentage of hydrogen in the treated gas stream. Next, for stripper, it is used to regenerate the absorbent into the absorber. This is to allow more absorption capacity per kilogram per unit. The absorption occurs when the tri-feed gas mixture with CO2 is fed to the absorber from the bottom, comes into contact with carbon dioxide lean absorbent or monoethanol amine to get a treated gas stream with higher composition of hydrogen gas and lower carbon dioxide composition. Then the heated saturated solvent is passed through the stripper. Carbon dioxide is stripped off by the stripping gas or steam that is fed into the stripper. Carbon dioxide lean absorbent feed stream is then regenerated into the absorber for circuit use. The concentrated gas stream with stripped CO2 is compressed for subsequent transportation and storage. Okay, for H2 enrichment unit, pressure swing adsorption process is used to adsorb impurities in the feed gas mixture to produce high purity of H2 as the last desired product. So high selective adsorbents and impurities are chosen, which are activated carbon and zeolite 5A. To increase the adsorption rate, for adsorption columns are used with cyclic adsorption processes through 4 cycles, which are adsorption, depressurization, regeneration, and repressurization. So the working process for PSA is the cyclic adsorption processes are first carried out in adsorbers A1 to A4. This PSA process works at constant temperature and uses the effects of alternating pressure and partial pressure to perform adsorption and desorption. First, adsorption is carried out at high pressure until the equilibrium loading is reached, and no further adsorption capacity is available where the absorbent material must be regenerated. This regeneration is done by lowering the pressure to slightly above atmospheric pressure, resulting in a respective decrease in equilibrium loading. As a result, the impurities on the adsorbent material are dissolved and the adsorbent material is regenerated. After termination of regeneration, pressure is increased back to adsorption pressure level and the process starts again from the beginning. Next, the table shows the flow of gases and processes throughout the valves contained in the PSA process. First, the pressure rise into the adsorber is gained by opening the control valves K1.1, K2.1, K3.1, K4.1 respectively, through which the gas is supplied to the adsorbent bed. Then, through valves K1.2, K2.2, K3.2, K4.3, the hydrogen product is removed from the adsorbers. The regeneration of the adsorbent bed works by flowing out the purged gas mixture through valves K12, K13, K14, K23, K24, and K34. Thus, the purging gas is discharged by valves K1.3, K2.3, K3.3, and K4.3 at the regeneration rate. To conclude, the PSA process is a continuous adsorption regeneration process which is controlled by alternating between high and low pressure at constant temperature. By having more adsorption columns, it helps in increasing the impurities absorption rate and allow a 99.9% of hydrogen purity in the top product as desired by the consumer.